entrance and you wrap around, and then you come up to head up 30th Avenue. And then you have, here's 30th Avenue. And Eugene's over here to the left, right?
So can we get an ortho on that?
Huh? Excuse me?
North is straight up.
North is up?
Yes,
Yeah.
north is straight up.
Okay.
Okay. So 30th Avenue, I-5's over here. Okay. So you're heading towards Eugene. And what happened when they, traffic engineers should have been fired that designed that curve back in the 60s. But what happens is, I think they designed this, I didn't go out and measure it, but I think they designed this almost as a circular arc, and then all of a sudden it goes into a straightaway.
Yeah, it does.
So what happens there is you come out of this very close to a circular arc, and then all of a sudden you're on a lane that is straight. And what happens is it tends to, the sense you get in an automobile is it tends to feel like it's going to throw you out into that next traffic lane. So how would a well-schooled traffic engineer design the curve? Railroad engineers do the same thing.
Yeah, to make it mellow out toward the end.
That's right. You make it mellow out towards the end. So let's say you're driving. You come into a curve, and so what you do is you design a segment. You design segments of the curve with, first of all, large radiuses of curvature, and then if you want to tighten it down, you then go into a new curvature that might be a shorter radius of curvature. And you can actually look at drawings and you can see these kind of lines like this. And so then you can make the curve as tight as you want, and what it will do is it'll force the vehicles and the drivers, usually with caution signs, to slow down 35 miles an hour, 15 mile an hour curve ahead. And so they'll gradually tighten the curve down so you don't get those abrupt shifts in their normal accelerations. Absolutely critical with railroad tracks. There's another great spot out here in Goshen. Trucks coming from Highway 58 towards I-5 that want to go southbound on I-5, they come underneath the freeway and then they turn around and have to do almost a 270-degree loop on a banking turn, and it's tight, and they have caution signs about the speed. And I live out that direction. I have seen in the last 18 years, I've seen probably at least half a dozen big rigs tipped over. Not dangerous accidents in particular, but the guys come on through in their big rigs and their big trucks, and they just make that curve a little too fast, and it just causes them to tip over, even on a banking curve. So railroads, absolutely critical that they very carefully design the curves on the railroads so that those top-heavy rail cars don't do the same kind of a thing. Okay. Let's do something a little more sophisticated than that problem. Oh, let's do something with polar. How about number 76? And I'll put the problem up here so people can see it. Robotic arm is elevating and extending simultaneously. So it's rising up and it's getting longer. And they've got quite a bit of information given to us here. So I'm just going to write all those numbers up on the board so we have something to work with. And then we want to compute the radial and transverse forces exerted that the arm must exert on the gripped part, which happen to have a mass of 1.2 kilograms. Compare the case with the static condition. Make sure we don't forget to do the static condition for comparison purposes. Okay, we're looking for radial forces and theta directed forces for that particular arm. Okay, so here we go. Here's all the prescribed information, including what we're looking for. And I think all we need to do is just write the darn equation. Should be pretty, this one's pretty much a cookbook problem, it looks like. So, sum of forces radially must equal the mass times the radial acceleration. And these terms that were prescribed for the robotic arm are part of our acceleration. So we're going to go ahead and write those in here. And I think they told us the mass was 2.2 kilograms.
No, 1.2.
1.2 kilograms. Thank you. And so we have 1.2, and our AR term is R double dot, which is going to be what up here? Here's the R.
It's going to be
So if you start cranking the derivatives on this thing, the constant here goes away. So it's just L double dot for R double dot. Is that right?
right.
Okay. So you differentiate this thing, and you got L dot, which is the telescoping effect, and then you got L double dot. So we have L double dot coming in minus R theta dot squared. R is this total length, including the 0.75 meters. So we have 0.75 plus L, and then our theta dot reading, I'm going to go ahead and write the general expression here first. So here's our scalar equation, at least the right side of it. Everything on the right side is known. Do I have a good free body here?
We need some forces on there.
We need a mass.
It's under the action of its weight. Now, what else? Anything else?
We talked about frictional force, but
Well,
that's what's holding it in place.
We can
there's, keep in mind, what we have going on here is we have a gripper. We have a
Yeah.
gripper holding on to it.
So it's squeezing it
Now,
on both sides.
it's squeezing it from, is it horizontal? Which way is it squeezing it? Does it
Well,
show in the book?
Kind of tilted vertically. and
Yeah, it
there's
looks
gonna
like
be
it's squeezing it this way.
Parallel to the R phase,
Yeah.
the R hat
Okay,
direction.
so it's squeezing the object like this,
Yeah, so that would be the
Okay.
theta hat direction, right?
right?
And because it's pushing it out, there's going to have to be frictional forces created there to move it in that direction.
Mhm.
For all we know, that could be a cutaway. So I don't know if we can.
Okay.
Well,
So, but what were they asking? Look at what they're asking for. They're simply asking for the radial force.
Right.
Okay. So we got all that stuff over there on the right side. All we have to do is drop the numbers in. And if somebody wouldn't mind, go ahead and punch that out.
Do you need to convert those degrees to radians?
Ah, thank you. Love that. Okay. So we have to drop in here the conversion to kick these into radian measure appropriately. Why do we have to do that?
Aren't the formulas determined?
Differentiation and integration you'd have to recalculate calculus if you use degrees.
Yeah, okay, well, that's part of it. And it also, it goes back to, we could simplify it by thinking of circular motion of what is arc length, you know, in a circular sense, related to a central angle theta. And you have, that relationship is this, requiring this to be measured in radians. And then for the derivatives, then you know cranking derivatives out, actually I'm going to write it as ds dt. This is linear speed. And this radius, remember, is if I take that radius, it's really equivalent to 1 radian of rotation. So radius values actually are conversion factors to convert angular measure into arc length. And you have to prescribe this in radian measure, the angle here. And so when you crank the derivative, and the reason that works, as you mentioned in the back, is that you have to, it's the limit of the difference quotient. And so you have to treat these angles as if they're real numbers. And radian values can be thought of in that fashion, as real numbers as opposed to degree measure, which is just an arbitrary way of measuring rotation. Okay, so back over here, when we drop these numbers in, we have our 1.2, we have our L double dot term, which is negative 0.3, and we have minus, we're adding an L value of 1/2, so this becomes 1 1/4. Add 1/2 to 0.75, and then our theta dot term, which we'll be squaring, is 40 degrees per second. So if we do that, we're going to have to take that 40 degrees per second and multiply it by pi over 180 to turn it into radian units, and then square that value. So if somebody would punch that up, I don't have this problem worked out. And be careful, both these terms are negative.
40 plus pi squared.
I'm sorry?
4 over 81 pi squared for our other
Well,
value.
okay, just the rest of it there.
I got negative 1.09. 1.09.
Negative 1.09. Anybody else punch that? Units. Whoops. Units or newtons? Newtons of force.
Do we have to contribute the weight of the object into it?
Ah,
I think that's where we're wrong, because
okay.
shouldn't it be the force from the arm plus the weight is equal to all of
We
that?
even drew it here. So what are we trying to figure out? I
The
gotta
force.
reread the question.
Force of the arm.
The
on the object.
radial and transverse forces that the arm must exert on the gripped part P.
Right.
So this is our mass P right here. So what we need to do is come back in here. We can keep that 1.09 if that's correct, and use it. And so we have a component of the weight that is this direction. Happens to be mg sine of theta, which was 30 degrees, so it's going to be half the body weight. Half the weight. So that's going to be 1.2 times 9.81 times the sine of 30 degrees. So that'll be half of the body weight, or 60% of 9.81. And that is negative in the negative R direction. So negative 0.6 times 9.81 plus the required FR force. So then this becomes additive. And the other value, 1.09, was negative. So we're going to get FR then is going to be positive 0.6, 9.81 minus the 1.09. Anybody else confirm the 1.09?
Yeah.
Okay, thanks. And that result then is approximately
4.796.
4.79,
Yeah.
and units on that are newtons. Now that's only 4 newtons, which is roughly a pound or so of force.
Well, it's only 1 kilogram for the objects.
Yeah, and the object only weighs, well, the object weighs, if the object weighs over a kilogram, that's more than 2.2 pounds, right? So you've got about a 1 pound radial force required there. Now don't forget, we'll finish this problem, and then we want to check the static situation, sort of see how this compares to the static. Okay, so let's keep going. So F sub theta must equal the mass times the theta directed acceleration. So we have our 1.2, and our theta directed accelerations, remember, was r theta double dot. So that's going to be our entire L, which is 0.75 plus, well actually it's the 0.75 plus L. Let's see, put that in there. Fix this. Times theta double dot plus the Coriolis term. Coriolis term was 2 r dot, and r dot is L dot, and times theta dot. We can drop the numbers in there, and then let's write our equations based once again on our picture. Let's see, in the theta direction, we have the other component of the weight. So we have the other component of weight that opposes the theta direction. So we have mg cosine of the theta, and then plus the other theta force, the remaining theta force, must equal this calculated value. So putting in the numbers, 1 1/4 on the length, theta double dot was, that's a third of, that's 2 pi over 3, isn't it? 2 pi over 3 here. Radians per second squared. I think I did that right. And then plus the 2 L dot is 0.4 meters per second extending times the theta dot, which is 40 times pi over 180. So we have a calculated value over there, and this term, the negative component of the weight, is the 1.2, the 9.81, and cosine of 30 degrees being square root of 3 over 2. So that becomes additive. So we end up with adding 0.6, 60% of 9.81 times square root of 3. And then plus this term, which is all positive, notice. Anybody have a value for this
The
dynamic portion?
Coriolis value is 0.67 pounds,
always in degree below.
0.67 newtons, and the other half, the other thought is going to be
Roughly two and a half or so, a little bigger than 2.5.
Oh, yeah, 'cause you're-
I got 0.558 for the dynamic part right there.
Well, the whole thing?
No, for just the 0.67. Where he says it's 0.67,
Yeah.
I say it's 0.558.
80% of this ratio, 2/9, 1/3, 2/3, 2/9, 2/3, 0.6, 0.8. I think this feels good. Anybody else punch it?
What'd you get for the whole
and
thing?
then Marge, the
The whole
0.558.
thing.
A whole
Sorry?
entire thing.
0.558.
Right here?
Line of crap is calculated.
And that's the Coriolis term alone?
The
Check
entire
that.
right part was 3.81 divided by
The whole
1.3.
thing?
3.81, yeah.
Yeah.
The whole thing?
It's just two, it's just the
Do
two
you want the
times-
do you want the mass multiplied into that number?
Yes.
Oh,
I got all that said and done, 3.812 basically.
see, he's right if you had the mass multiplied. I'm right if you had the mass taken out of it.
Okay.
I intended mine with the mass in. Which one did you want?
Oh, you're fine.
You guys gonna blame us or what?
You both are good. Okay. Okay. So anyway, the net result of that dynamic effect over here is this, right?
Yes.
Okay. And then we want to add this to it to get our final F sub
I
theta.
got 14.005, which is about 14 newtons.
So 14 newtons. Okay. Now, it said compare the FR and F theta terms with the static condition. So the static condition would be the arm sitting there at 30 degrees with the weight being 1.2 times 9.81, and then just decomposing that into its two components, which would be a static component here, FR, and a static component here, F theta, both of which look like they would be negative, because R hat is this way, theta hat is that way. And we know that this angle right here is 30 degrees. So F sub theta, static, would equal negative.
Aren't we looking at the forces that the arm has to exert not being exerted on the arm?
In the static, it's the same thing.
Yeah, let me just finish this and then we'll,
Okay, yeah.
yeah. Okay, so if I take the negative cosine reading of the weight, square root of 3/2 on that. That would equal that product, which is 0.866 times this, which is about 8.6 times that, about 9 point,
10.
About 10?
Which is
Excuse
just
me?
the left part.
10 point what?
19.
I got,
Hold on, did I do that wrong? No?
You guys should all be getting the same result.
Okay, yeah, I did it right, don't you?
that's, I'll try it again.
Negative 1.194.
We can all consistently get the same result.
Negative
on this problem. There's no
10.19.
reason-
And we're not.
If we were, there's no reason why we should be in
Yes,
class.
10.19.
Thank you. And then the FR term, static. Is going to be negative also. The sine term, that's going to be half of this, 60% of 9.81, which is roughly 5.6 or so.
Negative 5.88.
Negative 5.88. So if you compare these results with the 14 positive on theta due to the dynamic effects, and the positive 4.8 compared to this negative FR term. You know, fairly significant difference there.
So did we calculate both times the force that the piece is exerting on the arm? Because what we just did,
Yeah.
if that thing, if you think about it, this thing is having to work to hold that little thing up. So it's going to have to push back up on it,
Yeah.
and you would have positive forces.
So what we're looking at is the FR force. Now the positive sense of it would be this,
Right.
right? And the positive sense of the F theta force would be this way. And
that's the way the arm's going to have to push to keep that thing from falling.
And that's the way, yes. So I'll tell you what, why don't we revisit this at the beginning of class tomorrow, and we'll see. Oh, I wanted to remind you folks, tomorrow night, right after class, 5:30, we have these guests coming from OSU. Highly recommend that you folks make it. It's going to be over right next to the Math Resource Center in room 161. Room 161. Several former Lane students. I'm not sure who's coming. I know Royal Mortier's coming, and several other engineering students are going to be here to talk about their transition and what they've been experiencing at the university. Okay, that's it.